was checking my Twitter. Oh, so like at this, I saw that just I needed it out or something. But I was fine. I get this newness is nice. You want to drop the right. I remember those things like how costly and a bunch of here's my you go to is that what well, I also got that too. But it was an online one. Also, I was like, oh, yeah. No, why? They're reselling those blocks. These blocks should be like big pieces of those. And I was like, I didn't convention a lot of that. And it's only a couple of words of this. So maybe a little different animation, but I want another challenge. So I could go to the side of that. So it's like 200 close to 50. How much would it be? No, this is the price. Something like that. Like if it's like 80 kilos, unless you can get it, give the standard line and get it. People were just open and minded. Yeah, I think that was it. Because they're kind of like all the time, just people do that. Yeah. This price at 150, and almost 200 bags. I just haven't. Oh yeah, and it was in later on Amazon. Like they have like singles, they were selling women a day, right? So no. You should have your my dash happy. I could have asked you just yeah. I think that's what I think for a little it's for the official website. So I did like I looked at it to services I thought shit here. Well, you you don't actually play them or anything. I used to play them, but you just like I like keeping them.
Oh, look at that. Just look at that. Oh, yeah. There's these moments. I do. I think
but it's you see it like down here.
no, don't say that.
I was like, but I'm like, I'm thinking about it, and I'm like, well, if I go with someone, it's not too bad. I was thinking okay, well, I linked that. So compared like 500 and it's all of the views. So, and I'm just like thinking about like, this is only not just only, but it's a decent amount of money. Because I was checking all the ones too. Most of these are like 1,000 per.
Hello, Professor.
Hey, how's it going?
It's all good, all good. So I have it on my laptop.
Okay, you want to connect?
Can I? Yeah.
Yes. Yeah, let me to do this.
Perfect. And then
I'll
I'll
give you some space.
I'll keep it quick for you.
Yeah, yeah. I need to switch to HDMI.
Perfect.
Yeah, so the audio is coming in from there, but I think Zoom people won't be able to.
Oh, Zoom people won't be able to catch me or catch the presentation?
Yeah, unless you want to join the Zoom call.
Say first. It is. Nothing is this year, video.
Oh, is it a hybrid class?
It's not, but
Oh.
I just do things like.
Yeah.
I could join the Zoom.
Yeah, yeah, let me give you the. Actually, it's on here.
Easiest way to help.
Yeah, so there's the ID number.
Oh, so I need to figure out how to join it. So.
Check it out on the library.
And I just
And last year was.
sign, do I need to sign it?
Probably, yeah.
Really-
I've restricted it, so it's just Fullerton accounts.
Issue is this isn't my laptop.
Oh, okay.
So actually, let me see the. It's only Fullerton?
Yeah.
Check on your question yet? Is out-
Oh, John should work.
But the-
You know his password.
Yeah, I don't know his password.
Okay. Okay, never mind. I mean,
Yeah,
we'll
it's
just
fine.
say it's the audio.
Or I could try logging on my own, but I don't want to waste time, so
Okay.
it's already 4.
Okay, no problem.
I can
Okay.
start, yeah.
Uh,
Oh, shoot, I should.
I'm gonna give you an intro.
Yeah. go ahead.
Alright, hey guys, it's 4 o'clock, let's go and get started. So actually, before we start today, we do have a presentation from Justin. So he is a member of Titan Rocket here at Cal State Fullerton. So I'll give the floor to him.
Okay, so I'll keep it quick for you guys. I want you, it's 3:08, right? 3:08? Yes, okay. Don't want to keep you from it. But so I'm the president of Titan Rocket. So I'm gonna present just we're looking for members for our senior design club next year. And also just members, anyone want to join, want to help out, wanting to see what's up with us. So I'm gonna go through, we have 4 sub teams, just gonna go through them and kind of what you should expect if you want to join the team for next year. So yeah, we're a senior design team at a club. We design, manufacture, and launch high power amateur rockets. So amateur rockets, they're leveled by A through Z. The higher you go, or through Z, the more powerful your motors are. Our competitions are level 3, so that's the highest power for amateur rocketry before you need to start getting like government licenses. So this rocket from last year is 14 feet tall, so more than double the guys. So it's pretty cool stuff. And we'll just go through each team. So we have airframe first. They're worried about the actual structural stability and safety of the rockets, so they work on the body tubes and the fins. And they do a lot of simulation work. So this software down here is called Open Rocket. It's an open source software. Anyone can download it and use it. It's just pretty accurate flight data. So you input your parameters, input what you want, input what you have, and it gives you pretty nice graphs to see what you could predict. So this one's a lot of SolidWorks, a lot of modeling, and a lot of just taking a CAD thing and trying to make it physical. And then now we have propulsion. So this one, they select the motor and make the motor mount. The motor mount is what holds the motor and connects it to the rocket. And the motor is actually what gives the rocket thrust. So this picture here is just kind of the way the motor is. It's a cylinder tube, the motor, and the way the rocket fuel is packed, the designs you make inside gives you a different thrust curves. And these are kind of fun to look into and research. We're keeping it simple. This is the one, this is the easiest one for us to do and the cheapest. So we're keeping it tubular. But so a lot of CNC manufacturing with this one. Oh, we have a video. I'll show you. This is our launch actually over the weekend, Saturday, just from this Saturday.
Didn't expect Saturday.
And then yeah. So it comes back down in one piece. That's kind of a foreshadowing for the next team. Sorry. Launch and recovery. So this is I'm on recovery. This is my sub team. So I'm making a little fun for it. It's just parachutes at the end of the day. Having fun with it. But so this one is all the anchor points for the rocket, connecting the tubes together. Parachute selections, working with calculations for drag on the parachute and the descent rates. So keeping it safe. We keeping it around 20 feet per second coming down. That's per competition rules. The competition we're going to, and just safe for all the components. A lot of this is water jetting and CNC work. And here's some testing that we've done this year, and I like it a lot because I like combustion and I like blowing things up. So this is actually done, don't tell anybody, but in-house. So if you hear a loud boom, it's probably me. And then I have another one from what we did last month. This one has sound, so watch out. Oh, it should have had sound. Wait, 1 second, I got you. Boom. There you go. But that's that. And then avionics. So this is our telemetry. So receiving and sending signals. So at different heights, we want to do different explosions, different activities. So we have a barometer in there, we have a gyroscope in there. So all avionics is reading signals at certain heights, certain things that need to get done, and then actually sending them and getting them. And then, oh shoot, we won't play that one. And then Titan Rocket, we want you. So we're looking for a senior design team for 2024 to 2025. Oh wait, that's this year. 2025, 2026, my bad. And then I have two links right here. Discord on the left if you want to scan it, and then an application on the right. So if you want to join the team, or application to join the team, it's on the right. And if you want to join the Discord, it's on the left. Any questions?
Can I give them your contact information?
Oh yeah, yes you can, please. You can email me as well, send me a message on Discord. I don't think he has my Discord, but I'm in the Discord. I'm the one making the announcements. So thank you. Kept it short. How long was that? Oh, 5 minutes. Okay. Any questions? No? We're good? Beautiful. Get back to class.
All right, thanks, Justin.
Thank you very much so much.
Yeah.
Have a good one.
Yeah. And so for those of you on Zoom, if you're interested, I know you couldn't see the slides, unfortunately. It was kind of the same issue as earlier this semester. But if you're interested in joining Titan Rocket, you know, I'll send Justin's information to everyone in the class so you can kind of you know, shoot him an email and you can check out the slides from there. But yeah. Titan Rocket's really cool. It's really exciting. They are relatively new team, but you know, they've made a lot of really rapid progress in short time. And so the fact that they're even able to launch, you know, just you know, the team I think was only formed maybe 2 or 3 years ago, which is pretty fantastic. Yeah, they do a really good job. So if you're looking for a senior design project, I know I've talked to some of you in advising, but you know, if you're looking to join a team, Titan Rocket is definitely a good one for sure. Okay. So let's get back to 308. Okay. So this is our last week before spring break. So we just have lecture today, lecture on Thursday. And so plan for today is we're going to start a new topic called the Fourier series. So this, I'm hoping to finish up this set of lecture notes this week, and that'll take us all the way to spring break. And then we'll resume when we come back. And so your guys' homework 4s were due on Sunday. So I will be grading that kind of before we leave for spring break. Homework 5 is posted. Now it's not going to be due until, you know, after spring break. Even when we come back from spring break, you know, you guys have a few days to work on it. So, you know, don't feel pressure to work on it over spring break. But it's going to be on these Fourier stuff. Okay. So today's lecture is going to be important for that. Obviously Thursday's lecture is going to be important. And then, you know, anything that we don't finish up, we'll finish up on Tuesday when we come back from. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So this week, you know, we are really kind of pivoting to kind of a whole new topic. So, you know, 308 is kind of a little bit of a challenging class just because, you know, we kind of jump around different topics a lot. Sometimes what we do today doesn't really have much to do with what we did kind of the previous day. And today is one of those days. And so today we're going over a concept called Fourier series. Right. And so Fourier series is all about frequency. And so I think to kind of motivate this discussion, to kind of start us out, let's talk about how sound works. Okay. Okay. And so by sound, you know, I mean kind of, you know, what you kind of perceive from your ears as sound, right? So kind of all the words and spoken stuff coming out of my mouth, you know, for those of you on Zoom, the words that are coming out of the your speakers, you know, that's what's considered sound. Okay. Now, sound is very complex. And so, you know, we are going to quite simplify it. We are going to simplify it quite a bit. But for the sake of our discussion here, we'll say that sound is consisting of kind of 2 main components. And so the first component that that comprises sound is volume. Right, so how loud a sound is perceived, and so kind of that video of the launch that Justin did was kind of very loud, and so that was a very high volume type of sound. And the other component of sound has to do with its pitch. Okay. So let's talk about these two things, and let's talk about kind of how we perceive them. Okay. Okay, so let's talk about volume first. Okay, so what we perceive as volume is kind of what we consider as kind of the harshness or kind of the loudness of the sound, right? So we have very loud sounds like rockets kind of blasting off, and we have very soft sounds like maybe like your cat is purring. Okay, and so the way different sounds are differentiated in terms of volume has to do with the amplitudes of the pressure waves that travel through the air. Okay. Because in order for a sound to kind of travel through the air and reach your eardrums, sound is nothing more than just kind of fluctuations in kind of the air pressure, as it kind of travels from one space to another. Okay. And so, oftentimes, I think when you perceive sound, you usually kind of see it as kind of an oscillating wave, right? And so, you'll have a graph that looks like this. The horizontal axis here is time. Okay. And then the vertical axis is usually pressure. Okay. Right. And so usually when we look at sound, sound is nothing more than just kind of fluctuations in pressure, over time. Okay. Okay. So there's this kind of very strong connection with, periodic functions, vibrating functions, and the sound that we perceive. Okay. Now volume, right? What's considered kind of a loud sound versus a soft sound has to do with the amplitude of these vibrations. And so, the amplitude is nothing more than just the difference between kind of the peak of the wave and kind of the resting pressure. Okay. So this kind of height right here, this is the amplitude. Which correlates to the volume. Right? So louder sounds are going to cause, larger distortions or much larger fluctuations in the air pressure versus softer sounds. Okay. Okay. So to kind of illustrate this, so let's think of like a loud sound. Okay. So loud sound, maybe looks something like this, right? With very, very large oscillations. And a soft sound, might look something like this. So you still have fluctuations, but because the magnitudes are so small, they don't appear as loud, or we don't perceive them as loud as the loud sounds. Okay. All right, so that's volume. So volume, I think, is quite, relatively kind of straightforward, easy concept to kind of to perceive, right? I think it's I think we kind of perceive volume of sound kind of in our everyday lives, especially if you use a computer, your phone a lot. The volume dial is something that we use on a daily basis, and so you can think of sounds as just kind of modifying the amplitudes or the peak to peak distances for the different sound waves. Okay. Okay, so let's talk about pitch now. So that's kind of the other component of sound, in terms of how we kind of perceive what a sound sounds like. Okay. And so pitch, we perceive pitch as, pitch has to do with kind of the highness or the lowness of how a sound sounds. Okay. And so I think, we can all kind of think of certain, certain examples in our head when we think of, a very low pitch kind of sound versus a very high pitch kind of sound. I told myself I wasn't gonna do that today, but I did anyway. Now I feel really embarrassed. Okay. All right. So let's look at some examples. So these notes are really old. You can kind of tell how old I am by looking at some of the examples in my notes. And so, I was growing up, I was a really big fan of The Dark Knight and Batman. And so, if you watch any Batman movie, you know that Batman really sounds like really rough and really low pitched, right? Okay. Versus a very high pitched sound, I think people can, can always kind of think of that, that one maybe cartoon character that had the really high pitched voice. So when I was growing up, the really high pitched character there was a cartoon character. His name was Alvin the Chipmunk. So I don't know if you guys know Alvin. Oh. Okay. So how does pitch kind of manifest itself physically in the sound wave, right? So because we know sound waves are nothing more than just fluctuations of pressure that travel through the air. Okay. A low pitch sound has actually a very low frequency. So you still have oscillations, but the the time in between kind of the peaks of the of the waves are actually quite large. And so you'll see kind of pitch and frequency kind of, interchange kind of in kind of music theory in this stuff. Okay. So for a very low pitch sound, may look something like this, where you have these kind of very slow, kind of gentle oscillations. Okay. And so because there's such large kind of, temporal distances between the peaks, that creates what we perceive as kind of a low pitch sound. Okay. Versus a high pitched sound, will have a very high frequency. So kind of these oscillations are going to occur very rapidly. So you're going to go from high pressure to low pressure very, very quickly in a high pitched sound. So it might look something like this. Pitch is separate from volume, right? So you can have a very loud and low pitched sound, and you can also have a very soft high pitched sound too, and vice versa as well. Okay. But that's kind of the two main characteristics of sound that I want you guys to kind of focus on. Is one is the amplitude or the volume, and two, which is the frequency or the pitch. Okay. In fact, I think we hear a lot of very high amplitude sounds coming from outside this classroom. I think I should say here. Okay, so I'm highlighting these two things because amplitude and frequency, these are kind of the two kind of big hallmarks of a periodic function. And so this unit on Fourier series and Fourier transforms, it's all about, how can we describe these kind of periodic functions, okay? And so if you look at the graphs above, right? So sound is nothing more than just a periodic function. You have oscillations of pressure that travel through the air, right? So the pressure is going to go up, it's going to go down, it's going to do so in kind of a regular kind of pattern. Hence, that's what we call a periodic function, okay? So let's define periodic function. Right, so the definition of a periodic function is any function where there's a fixed value, we'll call it a constant p, where the function is going to repeat itself over that interval. So we have f of x is equal to f of x plus p, okay? And so this is true for all values of x. And so, it doesn't matter, where you are, as long as p is constant, then the function value is going to repeat as long as you have a periodic function, okay? So this p, there's a reason why I kind of call it p. This p here is the period of the oscillation. Okay, so that's the amount of time that's needed for the periodic function to repeat itself. Okay. So that's a fundamental kind of importance for a periodic function is so you know what the period is. Okay. And related to the period is the frequency, right? So oftentimes, when you think of a periodic function, sometimes you state the period, but oftentimes you express it in terms of its frequency. Okay. And so frequency and period are quite related to each other. And so for frequency, since we're using the symbol f for the function, we'll use kind of the traditional symbol omega for frequency. Okay. So frequency is nothing more than just 1 over the period. Okay, so the reason frequency is the one that's usually expressed is that you can use this frequency and plug it into a sinusoid. Right? So kind of the most classical example of a periodic function, of a repeating function, are sine and cosine. Right? That's kind of our bread and butter. And so a typical periodic function might look like this. So we have A for the amplitude multiplied by sine of omega times x. Okay. So this is a typical periodic function. Where this A here out in front, so the A is kind of this coefficient in front of your sinusoid, that is the amplitude of the oscillation. And this omega here, this is the frequency. Okay. So that's how those two quantities kind of come into play in the sinus. Okay. And those are exactly the two things that we talked about today. So amplitude, remember, that's the volume of the sound, and frequency, that is the pitch. And so, in a lot of ways, people say the building blocks of a periodic function is you need the amplitude and you need the frequency. Okay, any questions on this so far? Okay. Good. All right, so that's our periodic function. Okay. Now, so you hopefully you guys have seen a periodic function before, or at least this is kind of more or less kind of straightforward. So where does Fourier come into play? Right. So the title of these lecture notes is Fourier series. Well, the Fourier series is kind of, you can think of it as a different way to express periodic functions. Okay. Because what we've seen so far is that if you know the period, if you know the amplitude, and if you know the frequency of a periodic function, that's basically most of the information that you need for a periodic function, right? And so the Fourier series kind of takes that idea and says that what if we express periodic functions in terms of its amplitude and in terms of its frequency? Okay. Because even with just that information is alone, right? So even if you didn't know if it was sine or cosine, you have a pretty good idea in terms of what that periodic function looks like. And in some ways, it doesn't really matter if it's sine or cosine. You know that this function is going to have an amplitude, so it's going to kind of go away from the origin by a certain amount, and we know its frequency, so we know how quickly that the function is going to repeat. Okay, and so kind of the exact function that you put there, either sine or cosine, doesn't really matter all too much. Okay, but Fourier series actually takes this a step further as well. Okay. And so with Fourier series, basically the idea is that you can take any periodic function, so not just sines, not just cosines, so you can take square waves, sharp waves, ramp waves, anything, as long as it's a periodic function, you can express that periodic function as a sum of sine and cosine functions. Okay. And so this statement right here, right? It's kind of it's at 4:27 on a Tuesday before spring break. So this statement, I think for me it took me kind of a few years for it to really sink in, but this is probably one of the craziest things that I've seen in kind of math in terms of any periodic function. It doesn't matter what the periodic function looks like, as long as it's repeating with kind of a set interval, then you can represent it as a sum of sine and cosine functions, right? So let me give you an example. Right. So a lot of the research that I do, has to do with cardiovascular fluid. So I'm working with patients that may have like heartbeats or cardiovascular conditions. But the one thing about heart flow is that, or blood flow, is that it is a periodic type of phenomenon, right? So your heart is kind of beating with regular intervals, and your blood is kind of pumping with terms of its flow and pressure, and it's repeating in regular intervals as well. Okay. So let's look at a case. Let's look at heart pressure. So if you plot out, right, so if you took a pressure probe and you stuck it inside your heart and you kind of measured it over time, I guess you don't even need that. You can just take a stethoscope and put it on top of your heart, right? Your pressure curve kind of looks something like this. And so it starts out and it kind of ramps up pretty rapidly, right? So in this first phase, that's when your heart is kind of beating. That's when it's contracting, okay? Then you have a period of when your heart is relaxing, okay? And so when the heart is relaxing, it kind of goes through this kind of, long delayed, kind of relaxation period, okay? So a little bit of trivia for you guys. So when the heart is pumping, so when your heart is pumping, that's when the pressure in your heart rises. We call this systole. Okay. So that's when your heart is kind of actively contracting, right? And then the period when your heart is relaxing, we call that diastole. Okay. So diastole is usually a lot longer. A lot longer than the systole, okay? Because it takes longer for your heart to relax. And you can kind of observe that right now. And so you can kind of, look, you feel your pulse, you'll hear that there's like a pump. The pump is kind of when your heart contracts, and there's usually a longer delay before the next pump, right? And so, that's the systole and diastole, okay? And press your doctor, next time you see your doctor, ask them, what's my systolic pressure? What's my diastolic pressure? They might press, okay? Okay. So your heart pressure, because your heart is kind of beating at regular intervals, this is a periodic function, right? And so if we kind of continue this graph to the right here, right, you're going to see this entire graph kind of repeat itself, again. Right. And then, we can kind of keep continuing this kind of on, right? So your heart pressure is a perfect example of a periodic function that kind of happens in practice, okay? So now, according to a Fourier series, right, we can represent this curve with a sum of sines and cosines. So if you look at this graph right here, right? So it's not the most complex graph, right? So there's a part where it goes up and a part where it goes down. But this doesn't really look like our sine and cosine curves, right? So if you try to look at our sine and cosine curves, maybe a cosine curve might look something like this. Right? Maybe a sine curve might look like this. Okay. But each sine and cosine kind of has a fixed frequency. And so, according to Fourier, we can kind of capture this heart pressure kind of exactly with a sum of sines and cosines, which is, kind of crazy to kind of think about. Okay. So let's see mathematically what that would look like. And so, so let's say we have our function. Okay? So we'll say our function f of t, that is our periodic function. So that might be our heart pressure, something like that. Okay. I've switched the variable here to t, but t and x are kind of interchangeable. Okay. And so according to Fourier, right, we can represent this as a sum. And so if we represent this as a sum, so our sum goes from n is equal to 0 to infinity. Okay. Now this sum is going to consist of sines and cosines. And so in something like this, we have an cosine of n t plus bn sine of nt. All right, so ft here, this is our periodic function. And then this component here, this is, it's an infinite summation. And of course, each of our components there, sine and cosine, those are our kind of, you could think of those as kind of like our building blocks. So we're kind of building up this kind of, periodic function by summing up sines and cosines. Okay. Now the kind of the operative thing that kind of makes this whole thing work are those A ends and B ends, right? So I've kind of neglected talking about those kind of on purpose. So these A ends and B ends, we call these the coefficients of the Fourier series expansion. Okay. And those are kind of the kind of what the most important thing is. Okay. And so no matter what your periodic function looks like, no matter what kind of funky stuff it might be doing, as long as it's periodic and as long as it repeats itself, there exists some Fourier series expansion where you can represent that function exactly using a summation of just sines and cosines. Okay. Any questions on this so far? Okay. All right, so let's talk a bit more about the coefficients. So that's kind of the most important thing about Fourier series. And so if you look at where the coefficients are positioned, right, and you kind of relate this back to our discussion kind of earlier in the class about what a typical function looks like, a typical periodic function looks like, right? Those coefficients are playing the role of the amplitude of that sinusoid. Okay. And so what this kind of expression is telling us is that, if we kind of manipulate kind of the magnitudes of each of these sinusoids, and we kind of do so in a very careful way, right? And so we basically amplify some coefficients and we kind of decrease other coefficients, and they're in a certain ratio given the function, then, that's what's going to allow us to represent any periodic function with this expansion. So let me give you kind of the formulas for each of these coefficients, and then we'll do an example so that you can kind of see that in action. Okay, so let's so there's a formula for AN and there's a formula for BN as well. So the AN coefficients, so these are the coefficients in front of cosine. Okay. And so this equals to 1 over pi integral from minus pi to pi of our function f of t cosine of nt dt. Okay, so you have to perform an integral, right? So we're basically integrating over the product of our periodic function and our building block cosine. Okay, where n here, I think, maybe I should have defined this n earlier. N here is just some integer, so it's either 1, 2, 3, right? So it's the integer in our kind of our infinite summation. Okay, so that's a formula for AN. So for BN, we have 1 over pi integral from minus pi to pi of the product f of t sine of nt dt. Okay. So very similar to our equation for an, except instead of cosine we have sine. Okay, and that integer n kind of plays a role there as well. Okay, and so there is a third formula, because oftentimes we have a kind of a separate formula for a0. Okay, so this is kind of the first term in the expansion, and you'll see in a second why we have this separate here. But for the first term in the expression, sometimes we compute this separately. And so this is 1 over 2 pi integral from minus pi to pi of just f of t dt. Okay. And so these three formulas here, these are the formulas for the Fourier series coefficient, for a periodic function. But this is actually specifically for a case when our periodic function has a period of pi. Or 2 pi, excuse me. Okay, so after this, we'll do an example so you can kind of see it all kind of put together. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example so you can kind of see how this works. Okay, so let's consider the following periodic wave, and we're going to look at a periodic rectangular wave. And so visually, it's going to look like this. So let me move it to the right a little bit. Okay. So our wave, there's going to be kind of a forward region here. And then it's going to go negative here. Okay. So it's kind of like this box wave. And this entire thing is just going to repeat just like this. Okay. All right, so mathematically, we're going to express it like the following. Okay. So f of t is equal to, so you can see here, this is a discontinuous function. So it's one where we have kind of sudden jumps in the solution value. And so we have to kind of define it in kind of a piecewise way. So this kind of takes us back a little bit to our discussion of step and impulse. Okay. So what we can say is that f of t is equal to minus k when so this is when t is between negative pi and 0. Okay. And then it's going to equal to positive k when t is between 0 and pi. So when 0 is less than t, which is less than pi. Okay. And so we can put those labels on the graph here. So you can see that the upper value here, this is going to have be positive k. And the lower value here, that's going to be minus k. Okay. So we have kind of an interesting, periodic function here. And so what we want to do is we want to compute. Let's compute the Fourier series coefficients for this periodic function. So that's A0, AN, BN for this periodic function. Okay, so we'll get expressions for each of the coefficients. I'll show you it. I'll show you kind of the first few terms kind of expanded out. And then just to prove it to you that, we can actually represent the square wave with sines and cosines, I'll go ahead and plot it for you on MATLAB. I think these computers have MATLAB, so I should be able to do just that. Okay. Okay, any questions on this? Okay, all right, so let's go ahead and compute the coefficients, okay? So to compute the coefficients, it's relatively straightforward. So we're just going to plug into our expressions above here, okay? So we have three formulas, one for A0, another for AN, another for BN. So it's simply just kind of plugging this formula in, plugging in our function into these formulas. So let's start with A0. That's kind of the easiest one to do. So you have A0 is equal to 1 over 2 pi integral from minus pi to pi of our function f of t dt. Okay, so we don't have any sine or cosine involved with this expression here. Okay. So all we got to do is plug it. But because our function here is discontinuous, we have to split this integral up into the two different intervals of our discontinuous functions. Okay. So let's split. So we're going to split this into two integrals since our function is discontinuous. Okay. So we're going to have one interval because we're integrating from negative pi to pi. So we're going to have one interval that goes from minus pi to 0, and then another interval that goes from 0 to pi. Okay. Okay, so let's break that up. So we have 1 over 2 pi. And then we're going to have one integral here from minus pi to 0. Okay. And so the value of the function within that interval is minus k. Okay. Plus another integral from 0 to pi. And the value of the function in that interval is just positive k dt. Okay, so k here is just a constant, and so these integrals here are pretty straightforward. Okay. And so if we apply that, we get 1 over 2 pi multiplied by integral of minus k is just minus kt, evaluated from minus pi to 0, plus integral of k is just going to give us kt from 0 to pi. Okay, so we plug those values in. We get 1 over 2 pi multiplied by minus k times 0 minus pi plus k times pi minus 0. Okay. So if we evaluate that interior, the first term is a little bit confusing because we have 3 negatives. But 3 negatives make a negative, and so in that first term we have a minus k pi, and in the second term we have a plus k pi. So we have minus k pi plus k pi. So both of those are going to cancel out, and so overall we get a coefficient of 0. So that is our value for A0. Okay. Now A0 isn't always going to be 0. It just happens to be 0 in this case. We'll talk more about A0 in a bit. But for this particular problem, the value for A0 is 0. Okay. Okay. Any questions on this? Okay, all right, so let's compute an. Okay, so let's write down our formula for an. So an is 1 over pi integral from minus pi to pi of f of t cosine of nt dt. Okay. Okay, so once again, we're going to plug in our function into this integral here. Now we do have a cosine here, and so that's going to need to factor into our integral. But just like we did with a naught, we're going to split this up into two integrals because our function is discontinuous. Okay. Okay, so if we do that, we get 1 over pi multiplied by integral from minus pi to 0 of minus k cosine of nt dt plus integral from 0 to pi of k cosine of nt dt. Okay, so there's a little bit more involved with the integrals in this case, but not too much more. At least we don't have to do integration by parts here. Because remember, k here is just a constant, so the k can be just taken out of the integral. And then we have integral of cosine nt, essentially for both. Okay. Okay, so let's go ahead and do that. So remember, the n here is an integer, and so that's one thing that has to come out when you do take the integration. Okay. So first one here, we have minus k times sine of nt divided by n, evaluated from minus pi to 0, plus k, same integral, sine of nt over n, but this time a value from 0 to pi. Keep in mind that n is an integer, and that's going to be important in a little bit. Okay. All right, so to kind of simplify this a little bit, I'm going to take k over n, since both terms have k over n. I'm going to factor that out, just so that we don't have to keep writing it. And then we're going to evaluate this at the integration bounds. Okay. Okay. So if we do that, we have k over n pi, okay, multiplied by. So we have minus sine of 0 minus sine of minus n pi. Okay. Plus we have sine of n pi minus sine of 0. Okay, I know there's a lot of negatives there, but I think I got all of them. Because there's a minus from that minus k, a minus from the integration, minus from the minus pi. Yeah. Okay. All right, so let's take this term and let's simplify. Okay, so we have 3 sine terms here, but 2 of them are just sine of 0, right? So a sine is a lot of things, but we know sine of 0 is just 0. So we can just kind of cross that out. Okay. So the first and last terms in this expression are just going to go to 0. Okay. Now we have sine of n pi, right? And sine of negative n pi is kind of the same thing. So, I'm just going to look at one of these. Now, we haven't specified a value for n yet, but we do know that n is an integer, so it's some whole number. So it's impossible to get some kind of decimal here. Okay, so since n is an integer, and so it can be any integer up at this point. So 1, 2, 3, 4, 5, 6, right? All the way up to 12,000. That's technically an integer as well. Okay. So since n is an integer here, I would also make the argument that this sine of n pi is also 0. Okay. Now, why is that, right? So we've already established that sine of 0 is 0, right? Now let's look at the situation where n is equal to 1. So if n is equal to 1, we have sine of pi, right? So what is pi? Pi is just a 180-degree rotation. You're still on the x-axis. So sine of pi also is going to be 0. Okay. Let's look at n is equal to 2. Okay. N is equal to 2, we have sine of 2 pi. Okay. 2 pi is one full rotation around kind of the origin. And if you kind of end up back where you started on the horizontal x-axis, sine of 2 pi is the same thing as sine of 0, right? Because sine is a periodic function, which is also 0. Okay. You can keep going. And so you have n is equal to 3, right? We have sine of 3 pi, right? 3 pi, that's a, what is that? That's a 540-degree rotation. So you go around once, and then you go around 180 one more time. Okay. Again, you're at the x-axis. So again, this is 0. Okay. So as long as n is an integer, right? And as long as the argument of our sine is just n times pi, an integer times pi, you're always going to be, either you're making a full turn or you're making a 180-degree turn. And so this is always going to be 0. And by that same token, right? Doesn't matter if you go positive or negative. And so if you do negative, that's just a clockwise rotation. This is also going to be 0, right? So both of these terms here, we can just say are just going to be 0. Okay. And so if all those terms on the interior there are 0, right, then we can make the conclusion that an, right, our Fourier series coefficients for our cosine terms are also going to be 0 for all n. All right, so far we don't have the most exciting problems. We have a0 is equal to 0 and an is equal to 0 for all values of n as well. But things pick up a little bit when we do the PNs, I promise. Okay. Any questions on this so far? Okay, all right, so let's do the BNs, and then you're going to see we actually get something non-zero in this case. Okay, so our BNs, our formula for that is 1 over pi integral from minus pi to pi of f of t sine of nt dt. Okay. So once again, let's go ahead and plug in our function here, which is discontinuous. And so we have 1 over pi multiplied by integral from minus pi to 0 of minus k sine of nt dt plus integral from 0 to pi of k sine of nt dt. Okay, so let's do this integration. So I'm going to go a little bit faster this time, just because we've seen a lot of these kind of simple integrations today. Okay. Okay, so if we do that integration here, we get 1 over pi multiplied by integral of sine is going to be minus cosine. So we have a k cosine of nt divided by n minus k cosine of nt divided by n. First cosine here, we're going to evaluate from minus pi to 0. Second, in a second term here, we're evaluating from 0 to pi. Okay. Okay. So once again, let's simplify this. So let's take k over n and let's kind of factor that out of our expression here. So that's going to simplify things on the inside. That way we can just focus on just the cosine term. So that's kind of the most important thing. Okay. So if I factor out k over n, then what we get from this is k over n pi multiplied by. Let's go ahead and evaluate these integration bounds. We have cosine of 0 minus cosine of negative n pi, okay, minus cosine of n pi plus cosine of 0. Okay. So let's simplify this a bit, right? So first thing we see here, we have cosine of 0, cosine of 0. So cosine of 0 is not 0. Cosine of 0 is 1. Okay. So this term is going to go to 1. This term is going to go to 1. Okay. So thankfully, we have something that's non-zero in this case. Okay. Another simplification I'm going to make is I'm going to make use of a trig identity here. Okay. Don't worry, this one's quite simple. And so we're just simply taking advantage of the fact that cosine here is an even function. Okay. We're going to talk a lot more, on Thursday about what an even function is versus an odd function. Okay. But since cosine is an even function, we can say that cosine of minus n pi is equal to positive cosine of n pi. Okay. Because even functions are symmetric across the vertical axis. Okay. And so, if we just take the minus of the argument, you just end up with the function all the same. Okay. And so if we do that, then this simplifies our expression quite a bit. And so I'm going to take 2 and kind of factor it out. Okay, so we have 2k over n pi multiplied by 1 minus cosine of n pi. And this is our expression for the b x. All right, any questions on how we got this expression here? Okay. All right, so let's look at that cosine of n pi, and that's something you're going to see quite a bit in this unit as well. Okay. So cosine n pi, and so remember taking into account that n is an integer here. Okay. That means this is always going to be, values of, either cosine of pi and all of its kind of, intervals from there. Okay. Okay, so let's look at cases when, let's say n is equal to 1. Okay. So when n is equal to 1, we have cosine of pi. And what is cosine pi? Cosine pi is -1. Okay. When n is equal to 2, we have cosine of 2 pi. Okay. Cosine of 2 pi is just 1 because that's just kind of one full rotation around the origin. Okay. N is equal to 3. We have cosine of 3 pi. Okay. Cosine of 3 pi is again -1. Okay. So hopefully you're starting to see a pattern kind of emerge. So let's do one more just for good measure. So when n is equal to 4, we have cosine of 4 pi. And cosine of 4 pi is just 1. Okay. So that term right there, that cosine n pi, is going to alternate between -1 and 1, depending on the value of n. right? And so in fact, you can kind of take this a step further. So when n is an odd number, so when n is 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, all those odd numbers, then, our cosine of n pi is going to be -1. But when n is an even number, so 2, 4, 6, 8, 10, 12, 14, 16, 18, I can count in case you didn't know, then our n cosine n pi there is going to be positive. Okay, and so a common way to kind of express this quantity, cosine n pi, to make it a little bit more clear, is to express it as -1 raised to the n power. Okay, right? That's a little bit more clear. It's a little bit shorthand in terms of what that term is going to be. Okay, and so the final expression for Bn in kind of its simplest form is equal to 2k over n pi multiplied by 1 minus -1 raised to the n power. All right, any questions on this? Oh, we got this here. Okay, all right. So last thing we're gonna do today is let's actually compute some of the values for B, and then we'll actually kind of see it in practice. Okay. So let's compute the first 5 values for B. And so the way that we're going to compute the values of Bn, we're going to plug in different integers for n. Okay. So let's start with n is equal to 1. Okay. So when n is equal to 1, our B1 in this case is going to be 2 pi or 2k over pi multiplied by 1 minus 1, 1 minus -1, which is 2. And so our B1 in this case is 4k over pi. Okay. Okay. And so let's compute B2. So let's plug in n is equal to 2. And so n is equal to 2 here. We have 2k over 2 pi. So the 2 is going to cancel out. Multiply by 1 minus. We have -1 raised to the second power, which is just 1. Okay. So now in that parentheses, we have 1 minus 1, which is just 0. And so our B2 here is just 0. So as n is equal to 3, let's just go ahead and keep trudging on. So n is equal to 3, we have 2k over 3 pi times 1 minus -1. So that's going to give us 4k over 3 pi. Okay. Next, we have n is equal to 4. B4. Okay. So you have 2k over 4 pi multiplied by 1 minus 1, which is just 0. Okay. Right, so hopefully you're starting to see a pattern. So all the even numbers of n for this particular problem our coefficient there is 0. Okay. And then one more for good measure. Let's do n is equal to 5. Okay. So you have B5 is equal to 2k over 5 pi, 1 minus -1. And so what we get is 4k over 5 pi. Okay. Okay. Now this continues, of course, so you can keep computing more additional values for n, but I think you guys kind of get the point. All right. So let's take these coefficients, and so that includes the a0s and the ans that we computed, and let's plug that into our Fourier series expression. Because that's kind of where we started with this entire problem. We wanted to represent this kind of rectangular wave as sum of sines and cosines. Okay. Okay, so because remember, for any periodic function f of t, we can represent it as a summation from n is equal to 0 to infinity of an cosine of nt plus bn sine of nt, okay? Okay. And so let's go ahead and plug in all of our expressions for a and b, okay? So for this particular problem, we know all the an's are equal to 0. Okay. And so we know right away that that first term there is going to go away because all the an's are 0. Now, that's just for this particular problem. We're going to do more examples later on where the an's are not equal to 0. But for this particular problem, we can cancel those out because we showed that, okay? And then let's plug in all of the non-zero values for bn and multiply it by the corresponding values of sine, right? So notice that the sine also depends on n. Okay. So once we do that, once we plug in, so we only had 3 non-zero values for bn's. We have b1, b3, and b5. That's going to complete our Fourier series expansion, at least for these first few terms. Okay. Okay. And so if we do that, we get f of t is equal to, so let's start with b1. So b1 was 4k over pi, okay, multiplied by sine of t, plus b2 is 0, so we don't have to worry about 2. Then we have b3, which is 4k over 3 pi times sine of 3t. Okay. B4 is equal to 0, so we don't worry about b4. And then finally, we have b5, which is 4k over 5 pi sine of 5t. Okay. Notice that as n increases, we plug in the corresponding value for the coefficient, but also the frequency in our sinusoid is also increasing as well. So we have first sine of t associated with b1, sine of 3t associated with b3, and then we have b5 associated with sine of 5. Okay, and of course this continues. It is an infinite summation for a reason, but we only just computed the first 3 coefficients here. Okay, but at the very least, this is kind of the start of our Fourier series expansion for this rectangular wave. Okay. All right, any questions on this? Okay, so last couple minutes here. Let me see if there is MATLAB on these computers. If not, then we can go early. Okay, so let me do this just really, really quickly. Should have started MATLAB before. But basically, I'm going to show you. So, remember our function in this case looked like a square wave, right? So our function looked like this. And so my argument to you with the Fourier series is that, these three sine functions, when you add them together with these coefficients, we're going to get a function that starts to approximate these square waves here. Okay. Okay. If MATLAB decides to open it. Okay. Because, it kind of seems like magic, right? Because, we all know what sine and cosine functions look like. And so, to say that they can represent kind of a function here with these very sharp edges and very sharp corners is very interesting. Okay. All right. So I need to go pretty fast here. So let me go. I'll just do this all in the console here. Okay. once MATLAB initializes. Okay, so I said T is equal to length space 0 to 10 with 100 intervals. Okay. Okay, B1 is equal to 4 divided by pi. B2 is equal to only B3. 4 divided by 3 times pi. So I'm basically assuming that k is equal to 1 in this case, and B5 is equal to 4 divided by 5 times pi. Okay, then we have our f is equal to B1 multiplied by sine of t plus B3 times sine of 3 times t plus B5 multiplied by sine of 5 times t. Okay, good, no errors. Let's do a figure. Okay, so if we plot t and f, that should give us our function here. Okay, so it's not perfect, so you can see here, and it would be great if I shared so Zoom people can see too. The Zoom people are just hearing me chant out incantations like a madman, right? So you can see here that once I've kind of plotted this function, if you look at MATLAB here, you know, that's exactly kind of the function that we have, right? You can see here that we're starting to approximate this this kind of square wave here, where the square wave kind of looks like this, right? So it's not perfect because, you know, we've only done 3 terms in this expansion, right? But we're starting to get there. And so if we added more terms to this expression, you know, we'd be able to approximate this wave a little bit more closely, okay? And so when we come back on Thursday, you know, we'll kind of continue with this discussion. We'll see what happens when we add more terms or subtract more terms, and then we'll go from there. So thank you guys for coming today. Thanks for staying a bit late just to kind of see me type into MATLAB. Hope you guys have a good day, and I'll see you guys on Thursday.
So you know what's wrong.
Yep, have a good one. Jose, do you have any final questions before I wrap up the Zoom call? Okay, all right, I will see you next time then.